Hello and welcome to a new video. I'm KStevMath, and in this video I'm going to talk about special right triangles. Special right triangles first show up in geometry and normally kind of in the middle toward the end, somewhere in there. And they are a pretty tricky concept, and I'm actually doing this video because it's a skill that we need to be able to remember for pre-calculus, and I'm doing a pre-calculus course with Math UC this school year, 2020 to 2021. So if you have any interest in doing a course like that with me, then please check out the link in the description. Also at the link in the description, or a link in the description, you can find a notes page, especially since there's triangles involved. So if you're going to take notes on this, so you don't have to draw out all the triangles, you can go to that website and download a free notes page, print it out, and then start up the video and follow along, and it'll be a really great time. Taking notes can be super important, especially on something like this where you'll need to remember it later to build off of it. So it's handy to have notes that you can look back at. But anyway, this is special right triangles. The first thing that we might want to ask ourselves is, what is a special right triangle? There are two kinds of triangles that we end up, for whatever reason in math, caring more about than any other kind of right triangle. And that is a triangle that has two 45-degree angles, as well as a right angle. And then a triangle that has a 30-degree angle, a 60-degree angle, and a 90-degree angle. And as far as why those are the two things that we consider special right triangles and not any other, I haven't actually researched it to figure out who decided to make them special or whatever, but I think at least the 45, 45, 90 is pretty understandable that this is a triangle that we're most likely to encounter in the real world while we're trying to do things. That because it basically splits a right angle in half, I can see how there would be a lot of occasions where we might need a 45, 45, 90 triangle as an architect or engineer or things like that. And I think 30, 60, 90 triangles are similar, and you're going to see why in just a second when we look more closely at a 30, 60, 90 triangle. I'll point out my thought process here. But these are our two types of special right triangles, and what happens is there are pretty cool relationships with their sides that we can use those relationships so that we can avoid using our calculator. We can get radicals as answers or fractions as answers instead of having decimals, and instead of having to use sine, cosine, and tangent, we can just know the answers almost immediately just by looking at the triangles. So let's look specifically at a 45, 45, 90, and then we'll look at the 30, 60, 90. Okay, so the easier of the two to work with is definitely a 45, 45, 90 triangle. And that has a lot to do with the fact that if we have two angles that are the same in a triangle, the sides that are opposite of them have to be the same as well. So we could basically come up with a situation here where we say, well, we have two legs on this triangle, right, that are equal. This side on the left here, let's say that I want that to be 1 unit long. Well, I automatically know that the other side here also, the other leg also has to be 1 unit long, because our angles and sides across from each other have a relationship of being the same. And so from there, all we got to do is figure out, what does that make the hypotenuse? And if we don't know, we can discover what the hypotenuse should be by using the Pythagorean theorem. If you don't remember how to use the Pythagorean theorem, link in the description to my video right before this of going over the Pythagorean theorem, so check that out. But the Pythagorean theorem says a squared plus b squared equals c squared, where c is our hypotenuse, a and b are the legs of our right triangle. So if I do 1 squared plus 1 squared, I get my hypotenuse squared. Well, 1 squared is 1, so 1 plus 1 equals 2, so c squared is 2. To finish that off, we square root both sides. So our hypotenuse for this triangle is the square root of 2. So what that ends up meaning is that for any 45, 45, 90 triangle we have, if we know what one of the legs are, we can use this kind of ratio of sides thing, because every 45, 45, 90 triangle is similar to every other 45, 45, 90. So they have a proportional relationship, their sides do. So we can use this then to get to answers quicker, and partially because it's so easy to recognize, hopefully, once you get the hang of it, 45, 45, 90 triangles, it really can make things faster for you. And the idea is going to be that instead of thinking of this as 1, 1 square root of 2, which is fine to think of it that way, we could think of it, our sides, as x's, to show that we don't know what our legs of our triangle are going to be. And then whatever the legs of our triangle end up being, we times that by the square root of 2, and that ends up being our answer. So we could test this out using the Pythagorean theorem. We could say, well, what if my sides are 2? 2 squared plus 2 squared equals c squared. 4 plus 4 is 8. It might not be obvious yet, but this is going to give us what we want. The square root of 8 simplifies by splitting up into square root of 4 times square root of 2. We can take the square root of 4 and get 2. So that's 2 square roots of 2. But wait, that's what our pattern here is. That if our sides were 2, then our hypotenuse should be 2 square roots of 2. Now it's a little trickier going backwards. If you know the hypotenuse and your hypotenuse has a square root of 2, that's not too bad. You just take off the square root of 2. But if our hypotenuse does not have a square root of 2, to work backwards, we're going to have to do the opposite, and instead of multiplying by square root of 2, we'll have to divide by square root of 2, which can cause, issues of its own, I suppose. So that's kind of the gist of a 45, 45, 90 triangle. Let's talk about 30, 60, 90 triangle. So to come up with a 30, 60, 90 triangle, we actually need to first think about an equilateral triangle. So an equilateral triangle has 60-degree angles for all 3 of its angles. And so that means all of the angles are the same size and all the sides are the same size. So we could kind of go about this a couple different ways to figure out the different side lengths. But because it basically is boiling down to this idea of splitting the triangle in half and then finding the 2 legs of this 30, 60, 90 triangle, let's think about the relationship between this side that's our hypotenuse and this side down here that is currently the base. Those both have the same measure, right? If I go all the way across down here at the bottom, that is the same length as this hypotenuse. So if I divide this triangle in half and put a right angle here, then what does that mean that this base part of my right triangle is? What is this part of our triangle going to be compared to our hypotenuse and our base? Well, it should be half of the length, right? So we could label this as a 1/2 down here at the bottom, but because as a general rule as human beings we don't like fractions, what if instead we say, well, this side can be 1, and then the hypotenuse should be twice as big as 1, which is 2. So that's where we get 2 of our sides from for our 30, 60, 90 triangle, is thinking about this equilateral triangle and saying, okay, the base of this triangle, this right triangle, has to be half as much as my hypotenuse. From there, we can use the Pythagorean theorem again. So to find this third side, we would need to do something like 1 squared plus b squared equals 2 squared. Notice we know our hypotenuse this time. So we're going to have to subtract this 1 over and get b squared equals 3. So then we square root both sides and get b equals the square root of 3. And we're going to leave it as the square root of 3. We're not going to bother getting the decimal, because as much as we can in math classes, we like to leave things as radicals and fractions so that we haven't rounded and so that we don't introduce a rounding error into our problem. So the simplest 30, 60, 90 triangle that we can get has sides 1, 2, and square root of 3. And it's important that we understand that the square root of 3 and the 1, it matters which place they are. That if we do find the decimal for 1, by the way, we get something that is bigger than 1. The square root of 3 is like 1.2 something off the top of my head. Is that right? Yeah, I think so. It's either 1.2 something or 1.7 something, and I'm not sure right now. Oh, it must be 1.7 something because square root of 2 is 1.2 something. Just do it on your calculator so that you know and you're not having to rely on me. But the point is that it is a number that's bigger than 1. And so that relationship I talked about with 45, 45, 90 triangles of, because those angles were the same, the sides across from them were the same sort of relationship is happening here, that the smallest side of my triangle is across from my smallest angle, and then the bigger leg, the square root of 3, is across from the bigger of those two not 90-degree angles, 60. And so if we do turn our triangle around so that the angles are maybe in different spots, then we would need to pay attention to which side we were labeling 1 and which side we were labeling square root of 3. Just like before though, what I'm going to do is I'm going to replace this 1 with an x, and then think about what that does to my other two sides. And this is going to be pretty important, I think, for you to have written down somewhere on your paper for as you look through problems that are similar to this. Okay, so that you can look back and think, okay, what do I do next? So this is going to be more complicated to solve because we have two rules as opposed to one rule with the 45, 45, 90. So the best case scenario here is that you know what the base is, the way I have my triangle oriented right now at least, that you know the smallest side. Because if you know the smallest side, it's simply a matter of timesing by 2 to get the hypotenuse, timesing by square root of 3 to get the other side. But if we know one of the other two sides, we're going to have to use division. So the hypotenuse, knowing the hypotenuse is the next easiest thing, because if we know the hypotenuse, we just need to half that in order to get the smallest side, and then we can use that number to get the third side. If we know that what's right now my height on my screen, if we know that, then we're kind of stuck with the same situation as in the 45, 45, 90, where we're having to divide by a square root to work backwards and get to our smallest side. So we're going to do a bunch of examples, kind of each scenario that you can have going on here. And this would be a situation where it might be really easy for you to make up other problems for you to use to practice afterwards. I kind of have one example of each different type that you would encounter. But this does go along with the Math UC curriculum for Precalculus. It's Appendix B, and as I was looking at Lesson 1 for Precalculus, which I'm going to start in about a weekish with my class, I noticed that it said, hey, if you don't remember how to do Pythagorean theorem or special right triangles, you should do the lessons in Appendix A and B. So I'm like, here we go, let's do Appendix A and B, and this is B. You didn't need to know all of that, but let's do some examples. Example 1, find the missing sides. So because we only know one of the sides, we wouldn't be able to just straight off the bat use the Pythagorean theorem. That's why these special right triangles are a cool thing. And if we do know how to use sine, cosine, and tangent, that is actually also an option of how we could find the missing sides. But because it's a special right triangle, and in particular because it's a 45, 45, 90, if I know the rule for special right triangles, it will be faster and easier for me to just use those rules. So remember the rules. We have two legs that are the same length, and that means that since this side is 5 at the bottom, this side on the left also has to be 5. That's one of our rules. The legs are the same length in a 45, 45, 90 triangle. The other rule is that the hypotenuse is square root of 2 times as large as the legs. And so since our legs here are 5, that means that the hypotenuse has to be 5 times the square root of 2. And that's it. That's our answer. I think that this is one of those things that can be like, wait, that's it? Like, that's all I have to do? Yes. The issue here is recognizing in the midst of a whole lot of triangles, the issue will be recognizing that what you have is a 45, 45, 90, remembering that you can use these rules, and remembering the rules whenever they haven't just been told to you. That's what makes this concept a little trickier. But right now, when we've just gone over it, my hope is that it seems fairly straightforward, like this one did. Example 2, find the missing sides again. We have a 45, 45, 90 triangle. Once again, it's oriented a little bit differently so that we're not getting too used to seeing the same triangle over and over again. But it is still a 45, 45, 90. This time though, we know the hypotenuse, and we need the legs. So the rule is the legs are the same, and the hypotenuse is square root of 2 times as large as our legs. So in other words, x times square root of 2 should equal our hypotenuse, which is 8 square roots of 2. Without even actually having to divide by square root of 2 on both sides, my hope is that you can see why x has to equal 8. But if you do need to work through that step of saying, okay, I'm going to divide by square root of 2 to get x by itself, that's fine too. Square root of 2 over square root of 2 cancels out because they're the same. And both of our legs here should equal 8. It's a beautiful 8 right there. So again, fairly straightforward because our hypotenuse looked like it should, right? It had a square root of 2 in it. And so it was really easy to think backwards, or hopefully it's easy to think backwards now that you've seen it and go, okay, I get it. It was 8 square roots of 2, and now I need to go backwards and it's 8. So let's see what else we can do that might make this a little bit trickier. So this example, again, I kind of rearranged the triangle so that it looks a little different. And so it is important for us to look at this and say, okay, which side do I know? Do I know the legs or do I know the hypotenuse? We know the hypotenuse because 12 is across from our right angle. So we got that to start off. Now let's think about our rule, right, for our legs is that if we knew our leg or a leg of our triangle, we'd times that by the square root of 2 and we would get our hypotenuse, which is 12. So working backwards, what I need to do is divide by the square root of 2 so that x equals 12 divided by the square root of 2. Now there's this thing we do in math where we don't like having square roots on the bottom. And so we rationalize the denominator, that's the phrase for it, we rationalize the denominator by timesing the top and the bottom of our fraction by the square root that's on the bottom. So if I do square root of 2 times square root of 2 on bottom, that gives me the square root of 4, which I know that the square root of 4 is 2. So on bottom, I'm going to be left with 2. On top, I have 12 times the square root of 2, which I can't actually do anything with. So that's going to be 12 square roots of 2. Now I can simplify these numbers that are outside my square root, the 12 and the 2. So this ends up being 6 square roots of 2. And that means both of our legs have a length of 6 square root of 2. And so one takeaway from this is that if somewhere in our triangle we're going to see a square root of 2, if it's a 45, 45, 90. So we're either going to see it as the hypotenuse or we're going to see it as both legs. The other takeaway is this is a bit trickier, especially because of having to rationalize and think through that process, which you might not have done super recently. So you might think about rewatching this one or coming back to it later and rewatching it and having it available to you as you look at problems of your own that you're working through, because this one I would say is the trickiest of these first 3 examples. All right, now let's look at 30, 60, 90 triangles. So it is a little bit more complicated and a little longer just because we have kind of 2 rules instead of what feels like 1 with 45, 45, 90 triangles. So here we have 30, 60, 90. We've got this 7 down at the bottom. 7 is our smallest side here. So 7 is going to equal x in our kind of template that we have from earlier of our sides being x and then 2 times x and then square root of 3 times x. Okay, so since we know that x is supposed to be 7, we actually can pretty easily come up with these other 2 sides using multiplication. The hypotenuse is supposed to be twice as big, so the hypotenuse here is 14. I can't remember if there is a word for this other side. The longer leg here is 7 times the square root of 3, which is 7 square roots of 3. So that would be our 2 missing sides. So this is definitely the easiest of kind of the 3 situations for 30, 60, 90, that we know the shortest leg or shorter leg. So we just have to multiply to get the other 2. Let's try another one. Hey, you've made it this far in the video. You've made it to example 5. We only have 2 examples left. Why don't you take a moment and congratulate yourself for how far you've come. And as you're doing that, hit that like button and make sure you're subscribed, because both of those things really help me out. And if you feel like you know what to do in this problem, pause the video, give it a try, and then start it back up to see if you're right. And I'd love for you to leave a comment and let me know how this went for you or how this is going for you, so that I can get some good feedback on how you're doing, because I want to know, how are you doing? Example 5, find the missing sides. we now know, so this is kind of turned over, and honestly I don't know that this is very proportional because I just kind of free-handed these triangles using PowerPoint, not like I drew these perfectly straight lines. Yeah, right. Okay, so we know the hypotenuse because we know what's across from 90. So in our template, I don't know how to pronounce that, from earlier. Okay, this is what we think of with our sides for a 30, 60, 90. The smallest side is x. The longer leg is x times the square root of 3, and the hypotenuse is 2 times x. So if the hypotenuse is 2 times x and is also supposed to be 10, then that means that our shorter leg should be half as big. So our shorter leg should equal 5. So if we know our hypotenuse, our first step is to half it, and that gives us our shorter leg. Then we take that shorter leg and we times it by the square root of 3, and that gives us the longer leg. So our longer leg is 5 square roots of 3. Again, I don't think that's too terribly bad. Once you get the hang of what the rules are, you've recognized which side is which, you remember the rule, it's not too bad. To me, just like with 45, 45, 90, the issue really ends up being when the side that we know is the one with the square root, and in the problem it doesn't have a square root, so that can throw us off. And that's what our last example here is going to be, I believe, is that the longer leg is what we know. It doesn't have a square root, and we got to use it to find the other two legs. All right, our final example here, example 6. We have a 30, 60, 90 triangle. What we know is that the longer leg is 9 units long. So let's think about our rules, right? That we have the shorter side is x. Hang on, let me switch my color here. Our shorter side is x. Our longer leg is x times the square root of 3. And our hypotenuse is 2 times x. If you hadn't already made this connection, we are always going to want to try to take whatever we know and use it to find the shorter leg first before we try to find the other piece. Because the way I have this written with x's, I don't know just from the rules how to take the longer leg and turn it into the hypotenuse. I'm sure we could figure it out if we really wanted to, but it's just not something that I have written out here. So I'm going to take the fact that I know that 9 is the longer leg, and I know that the longer leg is square root of 3 times as large as my shorter leg, and I'm going to use that to find the shorter leg. So this is going to look like what we did earlier on the 45, 45, 90 triangle, where we say x squared root of 3 equals 9. So what does that mean that x equals? So I'm going to divide both sides by square root of 3, and we will have to rationalize again so that we can keep our square roots and our fractions and get the most exact answer possible. So to rationalize, we times the bottom by the square root of 3, which means this is 9 square roots of 3 over the square root of 3 times the square root of 3. Anytime it's the same number under your square root and you're multiplying it together like this, it basically just cancels out the square root, which honestly is exactly what we wanted. That's why we rationalized it. And then because 9 and 3 are something that divides, we should divide those, and we get 3 square roots of 3. So that means that our shorter side here, our shorter leg, is 3 square roots of 3. Now we need our hypotenuse, which is twice as long as this shorter leg. So what does it mean to be twice as long as 3 square roots of 3? The way we do this is we multiply the outside numbers together. 2 times 3 is 6, so we get 6 square roots of 3. So our hypotenuse is 6 square roots of 3. And that's how we do it. Again, this might be something that you want to rewatch or come back to later as you're working through problems yourself, because this one is a bit trickier than the other ones, at least in my opinion, for whatever that's worth. We did it! We made it through special right triangles! Hooray! Give yourself a pat on the back. So like I said, this is part of a pre-calculus course that I'm working through this school year. If you would like to join me in working through that, it's through a homeschool co-op here in the Pacific Northwest, but it will be available. Everything you need will be available online. So there's a link in the description. If you're interested in that, you can head there and check it out. And just also thank you for watching. For whatever reason, whatever made you watch it, and it is still making you watch it, thank thanks so much. It really is awesome to get to help you with math, and hopefully you will subscribe. Hopefully you will like the video, leave me a comment to say hi or to ask a question or whatever it might be. And feel free to check out my website, KStevMath.com, for other resources that you can use as well. Thanks so much.